In this video, I'm going to talk through the 2018 higher level question on the Leaving Cert. One thing that we got to keep in mind is we're not really looking for the answers on what came up, we're looking for the answers on what's going to come up in the next exam, the one that we're going to do. So when you're looking at these questions, they often give some good notes and some background, and that background is worth studying because first off, they could ask you the question directly from that, and second off, just for interest and grounding, because the question is always going to stay on a particular aspect of the course. So while you could technically skip over that introductory material, it's good to look at to get an idea of what's going to come up, and it'll frame the question then to follow. So the beginning of this question gives some good notes. So first off, it tells us momentum, energy and charge are conserved in nuclear reactions. So that's a key thing, and it's also just kind of nicely and shortly stated there. Second off, in beta-decay, an unstable nucleus emits an electron. So we looked at that conversion before. So the unstable nucleus emits an electron and gains the extra proton because the neutron within the nucleus decays in that way. Then for the background, in the earliest 20th century, it was found that momentum and energy did not appear to be conserved during beta decay. To solve this apparent problem, Wolfgang Pauli predicted the existence of an unknown particle about which he said, "I have done a terrible thing. I have postulated a particle that cannot be detected." You'll find more about Pauli in the attached document, and it's worth going through them to try and learn these guys and to see what they look like, what they said, and get an idea for their personalities. So Pauli predicted the existence of the neutrino, and the neutrino accounted for the missing momentum and energy. So that's the question that comes from it. So that's one of the key ones. It's asked a lot of different ways, a lot of different times. So Pauli predicted the existence of the neutrino. The neutrino accounted for that quote-unquote missing momentum and energy. And when you account for the neutrino, both momentum and energy and charge and everything else are confined and are conserved as they should be. So next they focus in on beta decay. So give the equation for beta decay. So again, our neutron gives us our proton and our electron and then this missing neutrino. So we wouldn't have looked at the neutrino previously in radioactivity when we were studying this, but that's what happens. The neutron disintegrates into a proton and an electron. That electron is emitted at high speed out of the nucleus. We can see our charge here. We have a positive charge on the proton. Sorry, that's mass. We have a positive charge on the proton, the negative charge on the electron. So the neutrino then must be neutral in order to conserve charge. So Pauli thought that this particle could not be detected as it had no charge and it had an extremely small mass. There's still kind of ongoing debates about whether or not it has mass, but it seems to have an extremely small mass. And again, extremely small by these scales are extremely, extremely small. So the neutrino eventually was found by Cowan and Reines in 1956, which is 25 years later. So despite that it barely interacts with matter, which is another thing you could say there, it doesn't really interact with matter, Cowan and Reines were able to detect this experimentally and prove Pauli's theory. So from then on everything could work on, so neutrinos exist. So again, while this wasn't asked, that is another common question: who discovered the neutrino? So on to the next one then, our next page of our notes. So pair annihilation is the next topic. So in pair annihilation, two gamma rays are produced as momentum must be conserved. So they ask us that why there are two produced. So the conservation of momentum is the reason that two have to be emitted. So the charge before is zero because you have the electron and the positron. They're annihilated in this reaction. And then the charge after is still zero because gamma rays have no charge. So therefore gamma ray charge is conserved in this. The maximum energy then they ask us for each photon. So for each of these photons produced, so that symbol there is the symbol for a photon in this collision. So we have then the electron, the regular electron, effectively no mass, but you can look it up in the tables and get at what it is precisely, and a -1 charge. This then is a positron, again zero charge with a +1. So -1 and 1 give me 0. So this is here 0 mass, 0 charge. So pair annihilation, this is our equation. We have the positron and the electron. They give us 2 EFs, so that's 2 electromagnetic radiations, so that's 2 gamma rays. So we then need our E equals mc squared formula, which is a safe bet in any of these questions. So the electron and the positron turn to energy, so this mass is multiplied by the speed of light squared, and that gives us the amount of energy that's produced. The second equation you'll need when you're dealing with pair annihilation is E is equal to HF. Now in this case you have two things colliding so that they're annihilating, and they've then produced 2 of these rays. So it's given by that equation there, the 2 rays. So here we have the mass of the electron by the speed of light squared. So we have to multiply those things in there. When you take those three and multiply them together, you get this amount of energy. So Planck's constant then, again given in the table, 6.626063 by 10 to the minus 34 and the unit joule of seconds. So this energy here that we calculated, so this mass which is turned into energy, that is equal to HF. So that's why I got those two formulas there. So this much energy has been produced. That energy equals 2HF, so we can divide across by 2H, so the frequency of each of these waves is equal to E. So we take the energy that was produced, which is up here, divided by twice Planck's constant, which is this, and we get the frequency then here. So the frequency, we can round that off then to 2 decimal places, so it's roughly 1.24 by 10 to the 20 hertz. Following on, the last part they have is, and again we can look this up on page 48 of the tables, two other negatively charged leptons are the muon and the tauon. So again, if you know it's there, it's very easy to just go look it up. So you got the muon negative and the tauon negative. So the three forces that leptons experience, which again a question you'll find in a number of places. So the three forces leptons do experience in decreasing order are the electromagnetic, the weak, and the gravitational. So that's the weak nuclear force there. They do not experience the strong nuclear force, which again they could ask that question in a different way. So the one they experience the most is electromagnetic, then weak, and then gravitational. So the largest down to the smallest. So again, this equation, you could do it a couple of different ways. You don't have to do it like this, but that does follow through. So twice the mass of the electron-positron gives you that energy. That energy then divided by twice Planck's constant, because you've manipulated your equation, then you get that frequency and you round it off. So that is the 2018 paper.